Hello everyone, welcome back. This is lecture 6 and we'll talk about chapter 7.5 Lagrange multipliers. Now Lagrange multipliers is very useful in computer science. It's often used in a lot of optimization algorithms. Now we won't go too much into detail here. I will not talk about why we employ Lagrange multipliers in some algorithms, why it's computationally efficient. We will just focus on the mathematics side of it. We'll give a definition of the Lagrange multipliers and we'll see how it's used to solve different optimization problems. Okay, first recall this example from the last lecture. At the end of the last lecture, we did this problem. Find the largest possible rectangular box with one vertex at the origin, which is 0, 0, 0, and the opposite vertex on the plane given by this equation, 6x plus 4y plus 3z equals 24. Now, here's how we solved it. We say that the volume is, suppose the opposite vertex has coordinate x, y, z, then the volume is x times y times z. And z, from this equation, we can deduce z equals 24 minus 6x minus 4y divided by 3. So this is the step of substitution. We substituted z, the z coordinate, with x and y, and we got an equation that involves only two variables, and then we said v partial x equals v partial y equals 0, and then we get two equations about x and y. Solve these, you get a couple points, and then you just check individually whether they are local max or min or saddle points. Okay, so now this is all perfectly fine, but we can also solve it using Lagrange multipliers. Let me do this. So we can also solve it using Lagrange multipliers. Now, Lagrange multipliers is a method that specifically targets these problems. What problem? It's called a constraint optimization problem. So the term is kind of self-explanatory. Optimization means we are trying to optimize something. In this case, we are trying to optimize the volume, finding the largest volume. And the constraint part is this constraint condition, the 6x plus 4y plus 3z equals 24. So mathematically speaking, this constraint optimization problem is maximizing x, y, z under the constraint 6x plus 4y plus 3z equals 24. Okay, so if we give a general form of the problem, it will be find the maximum or maximize or minimize x, y, z. No, let me first give a 2D version of the problem, two-dimensional version of the problem. Maximize, minimize fxy under the constraint some function g of xy equals 0. Okay, and similarly the 3D version would be just maximize f xyz under g xy z equals 0. Okay, where f and z are some functions. So this is a constrained optimization problem. And the method of Lagrange multipliers is, so first we have the theorem. This is probably called the theorem of Lagrange multipliers. It tells you when the maximum or the minimum of this constrained optimization problem, or when the maximum or the minimum happens, and then from this theorem you will see immediately how to proceed and find these max and mins. So the theorem is this: if f of x and y has max, min, subject to g x and y equals 0, then the max or min will occur at one of the critical points of the function big F, capital F. It's different from little f, so it's some other function we are creating right now that depends on x and y, and another extra variable that we create called lambda, and this is defined by the way, when I write column followed by equal sign, it means this is defined by whatever's on the right. Equals little f of x and y minus lambda times g of x and y. So we multiply the constraint by a variable lambda and subtract it from our function f, and we claim that the maximum or minimum of f will occur at the critical points of this capital F. Okay, and similarly, if it's a function in three-dimensional space, if we have variables x, y, z, then so if say f depends on three variables, so maybe I should say this. If f of x, y, z is, stop. So this is the similar. So let me just write this again. This is the 2D case, and the 3D case is the same. 3D case is now our little f and big F are are functions of three variables x, y, z. We similarly define our capital F of 4 variables, x, y, z, and then lambda, equals f of x, y, z minus lambda times g of x, y, z. Okay, and then we again look for critical points of this function. All right, so this is the theorem. Now, how do we use the Lagrange? How do we use this theorem to find the local maximum or minimum? Simple. Now we know, given this theorem tells us that these local max or min occur at the critical points of this newly created function capital F. So we only have to find the critical points. And to find the critical points, like always, we take the partial derivatives and set them to 0, and then we find all the critical points. And now, so we say that max or min occur at critical points. It doesn't mean every single critical point is a local maximum or minimum. So we have to check all of these critical points individually. So to write it down, the process is this. So first you create our capital F like this, and then to find critical points, so the first step is find critical points. And that's given by f partial x equals f partial y equals f partial lambda. Note that lambda is not a constant, okay? It's a variable. So our capital F is a function of 3 variables. So f capital lambda equals 0. Okay? If if f is a 3-dimensional case, then we have 4 equations. F partial x equals f partial y equals f partial z equals f partial lambda equals 0. All right, and the second step is find the value of f at each critical point. Note that these critical points refer to the critical points of big F, capital F, not little f. Okay? But we evaluate the value of little f at each critical point of big F. And we find the largest or the smallest. Depending on if you're looking for a maximum or a minimum. Okay, so here's how we use Lagrange multipliers to solve constrained optimization problem. All right. So this process seems a little arbitrary. So we're just we're multiplying our constraint by a new variable lambda and subtracting it from our little f for no reason at all. So let me give you a quick explanation of why this works. It's not a formal proof, but it gives you an idea how this method was derived in the first place. Okay, Now suppose, first of all, suppose we're looking for maximum, okay? Now suppose our little f has maximum say f of x naught, y naught equals some constant, equals some number c. Okay, and we look for what we do next is we look for the contour map of little f, and we look for the contour map of G. Suppose this is the contour map. Why didn't I start in the middle? Okay, we're talking about two-dimensional case just because it's much simpler to draw. Alright, so suppose the contour is something like this. To make it simple, let's assume the contour curves of f are circles. So things like this. So you get a bunch of contours, and let's say the inner one. So there must be a contour defined by f of x and y equals c. Right? Okay. Now we also have the curve given by g of x and y equals 0. Now the claim is that g of x and y, this curve, say it looks something like this. Not a very good idea. Yeah. Probably shouldn't intersect at the x-coordinate, just because it makes it messy. Okay, sorry about that. Suppose we have a curve defined by g of x and y equals 0. Now the claim is that this curve g of xy equals 0 and this curve f of x and y equals c must be tangent to each other at some point, and that point is x naught y naught. Okay? Well, why? So the idea is, suppose that it doesn't intersect. For example, if the curve looks something like if the curve looks something like this, if this is the g of x and y equals 0, then you have a problem, because since it's not tangent with this contour curve, then you can find some other curve that's tangent to it, and that contour curve will have a smaller value. So that's what's the problem here. Because to find the minimum of f, while under this constraint, that means it's the intersection of these two curves. Now, if these two curves are not tangent, you can find some other contour curve that intersect with g of xy equals 0, and the points on that contour curve will have have larger f value, and that creates a problem because it contradicts with our assumption that c is our maximum value. I hope I've explained this. So let me write down the claim here. F of xy equals c, and g of x and y equals 0 must be tangent to each other. Okay, so I probably shouldn't write f of x now, y not equals c. Let's just say f of xy has maximum value c. So we don't get confused. The x naught, y naught is not predetermined. It's the point obtained from this claim. At some point, and let's denote that point by x naught, y naught. Okay, so we figured out that the curve f of x and y and c equals c, and g of x, y equals 0, they're tangent at this point. Now, what does that tell us? One interesting side note, or not side note. So one background you need to know is that one background lemma you need to know is that if you take the gradient that is the vector df dx, d partial f d partial x, d partial f d partial y, evaluated at say x naught, y naught, this is also written as, sorry, let me rewrite this so we don't get confused. This is the notation for the gradient. It's an upside down triangle, and evaluated at x naught, y naught. This is defined as the vector f partial x, x naught, y naught, and f partial y, x naught, y naught. This is perpendicular, or say usually the better term is normal. This is normal to so that means at this point everything's squished together somehow. At this point, you get a vector that's pointing outwards, and that vector is gradient of f at x naught, y naught. Okay, so that's the gradient of f, and it is normal to this contour curve f of x and y equals c. Normal means like perpendicular, but this is the contour curve is not a straight line, right? So when you say normal to a curve, what you imagine is if suppose you have a straight line that's tangent to this curve here, then this point this vector is said to be normal to the curve if it is perpendicular to that straight line. Okay? So if we use the lemma, we know grad f is normal. So I'm just repeating this is normal to f of x y equals c at the point x naught y naught. And if you apply this lemma on the function g, then you will realize grad g evaluated at x naught y naught is normal to g of x and y equals 0. It's just applying this lemma onto g. So we're just replacing f with g, and we get this. Okay. Now we know the grad f and grad g are normal to f equals c and g equals 0 respectively. But we also know these two curves, f equals c and g equals 0, are tangent. But this is not 0, this is c. Right? This is tangent. So, since we know they're tangent, we know grad f and grad g are parallel. Just imagine this. If you have two vectors that are normal to two curves that are tangent, then they must be parallel. So these two gradient vectors are parallel. This is not how you spell parallel. I don't remember how to spell parallel. Maybe like this. Either way, these two gradient vectors are parallel to each other. And mathematically, that means, oops, gradient of f equals gradient, equals some number lambda times the gradient of g. That is how we write parallel mathematically. So if two vectors are parallel, then one vector must be a constant multiple of the other. Okay? And remember that gradient is partial with respect to x and then partial with respect to y. So if you write that out, you find f partial with respect to x evaluated at x naught y naught equals lambda times g partial x naught y naught, and f partial y x naught y naught equals lambda g partial y x naught y naught. And then of course is the last equation, which is just g of x and y equals 0. That's given in the problem, right? So we end up with three equations, and these equations are exactly the partial derivatives so yeah. One moment. I should say this. So these three equations tell you exactly that x naught, y naught, and this lambda we're looking for is, so I should write maybe this is lambda 0, lambda naught, okay, is a critical point. Of big F. And remember that big F is defined by little f of x and y minus lambda times g of x and y. Why is that? It's very straightforward. You just you just perform the simple partial derivatives on big F. So suppose you take the partial with respect to x. What do you get? So since big F partial x equals little f partial x minus lambda times g partial x, and f partial y, but what is z? I meant lambda. Equals f partial y minus lambda g partial y xy. And lastly, f partial lambda, notice that little f has nothing to do with lambda, so it's just a constant in terms of lambda. Therefore, when you take partial derivative with respect to lambda, you just get minus g of x and y. So it corresponds to exactly these three equations. When you put in x naught, y naught, z naught, it means this, since it's a critical point, it means f partial x of x naught, y naught minus lambda times g partial x of x naught, y naught is 0, which gives you the first equation. And similarly, this, when you plug in x naught, y naught, lambda naught, gives you the second equation, and this gives you the third equation right here. So this is the sketch of the proof for the method of Lagrange multipliers. Okay, now that we've seen why the method of Lagrange multipliers is true, let's do a couple practice problems. The first one, let's go back to our starting example, which is the one with the rectangular box with one origin, with one vertex on the origin at the origin and the opposite one on the plane. So that problem, the rectangular box problem, that problem is equivalent to if you get rid of all the words and write it in the math language, then that problem is equivalent to maximize xyz subject to uh, 6x plus 4y plus 3z minus 24 equals 0. This is the expression for the plane. All right. To solve this, well, first of all, what is our f and g? Our f is, as a function of x, y, z, is, well, x times y times z. And our function g of x, y, z is 6x plus 4y, oops, plus 3z minus 24. From this, we get our expression for the big F, which is f x and y and z and lambda, equals little f minus lambda times g, which is xyz minus lambda times all of that. Distribute the multiplication, we get minus 6x lambda plus 4y lambda, and then plus 3z lambda minus 24. Alright, take the partial derivatives. F partial x equals yz minus 6 lambda, and then f partial y equals xz plus 4 lambda, and then f partial z equals xy plus 3z. And then finally, f partial lambda equals minus 6x plus, okay, I am doing something wrong here. Oh, my bad. Yeah, I did something wrong. So this is supposed to be inside of parentheses because g times lambda is this. So I need to change the signs of these terms. It's minus 4 lambda and then minus 3z. And finally, this is not 24, but 24 times lambda. That is a lot of arithmetic mistakes. Minus 24 lambda. Yeah, like that. So minus and minus becomes plus 24. Okay, oh, what? I meant, sorry. Minus 6x, then minus 4y, minus 3z, then plus 24. And all of them equal 0. Why do I keep writing stuff like this? This is 3 lambda. Okay, let's solve this. We have 4 equations, 4 variables. From the first equation, we get that six lambda equals yz. So lambda equals yz divided by 6. Second equation gives us lambda equals xz divided by 4. And third equation tells us this is second, this is third, this is fourth. Third equation tells us lambda equals xy divided by 3. Okay, now from these, so we and since all of them equals lambda, we get an equality yz divided by 6 equals xz divided by 4 equals xy divided by 3. Now look at the first the first equality, yz divided by 6 equals xz equals xz divided by 4. We get, let me just write this. So this is the first equality, and then we will get the second equality, which is yz divided by 6 equals xy divided by 3. Okay, now so since in the first equation there's a common factor z, so let's divide z on both sides. We get y over 6 equals x over 4, and multiply both sides by 6, so you get y equals 6 over 4, which is 3 over 2x. Similarly, for this one, divide y on both sides, we get z over 6 equals x over 3. Therefore, z equals 2x. And plug everything into the fourth equation. We get minus 6x minus 4y times 3 over 2x, so minus 6x. And then minus 3z, again minus 6x, plus 24 equals 0. So minus 18x plus 24 equals 0, 18x equals 24, x equals 24 divided by 18, which is x equals 4 over 3. And since we have the relationship between y and x and then z and x, we get y equals, multiplied by 3 over 2, we get 2, and z equals 4. So we get only one critical point of this equation, then that must be the maximum we're looking for. So we have the volume xyz equals, what's the answer for when you multiply this? You get 32 over 3. Oh, I made a mistake here. Z equals 2x, so that's 8 over 3. So that's not 4. Z is 8 over 3, and then if we multiply these together, we get 8 times 8, 64 divided by 9. Alright, so we solved the same problem but using a different method this time. Now you might be wondering why we need Lagrange multipliers at all, aside from the computer science reason that I mentioned at the beginning, because it seems that it's not so much easier than substituting. So the before in the last lecture, what we did was we substituted z with x and y into the original equation, x times y times z, and use partial derivatives to find critical points of that. So it doesn't seem like Lagrange multipliers improved the process a whole lot. But actually, under some circumstances, this is actually easier to compute. For example, in this problem, you'll realize that the substitution method gives you very messy equation, while the Lagrange multiplier is much more succinct. So here, let's maximize. This example is a problem of 2 variables only. Okay, so let's maximize. Two x plus 3y on the unit disk. The unit disk is the circle with radius 1 centered at the origin. So it's x0 plus x squared plus y squared equals 1. Okay? In this case, if we solve it by using Lagrange multipliers, then our f of x and y will be 2x plus 3y. And g of x and y equals g of x and y equals x squared plus y squared minus 1. So this is how we, and then we go through the same process and then use the method of Lagrange multipliers to solve this. Now, if you were to do this using the substitution method like we did the last time, you are going to end up with a very messy equation because, for example, in this case, if you substitute y with x, you get x equals square root of 1 minus y squared. And if you plug it back into the 2x plus 3y and take partial derivatives, you're going to end up with something at least more complicated than what we're going to get from the Lagrange multipliers. So this is an example where the Lagrange multiplier method is simpler or easier than the substitution method. Okay, let's see how that works out. Now we have our f and g. We are going to define our capital F as a function of x, y, and lambda. And this equals, again, let me write out the formulation, which is f minus lambda times g. So you get, oh, what is equals 1? I meant minus 1. Because we use the constraint g equals 0, that's why we have the minus 1. If x squared plus y squared equals 1, then x squared plus y squared minus 1 equals 0. Okay, so this is our g, and then our capital F will be 2x plus 3y minus x squared lambda plus y squared lambda minus lambda. Okay, then the partial derivatives. Equals 2 minus 2x lambda. And partial derivative, let me leave some space here because we're going to write some calculation here later. F partial y equals 3 minus 2y lambda, and once again, leave some space in between. F partial lambda equals x squared, minus x squared minus y squared plus 1. Right? So like I said, you immediately see the advantage of this method over substitution because this time when we take the partial derivatives, it doesn't involve square roots and all of that. As a comparison, if you use the substitution method, like I said, you will have x equals square root, actually plus minus square root of 1 minus y squared. And when you take the derivative of that, you get square root on the denominator and all that mess. So you see this, in this example, the Lagrange multipliers are much easier to use. Now when you set these equal 0, from the first one you get, since 2 minus 2x lambda equals 0, then 2 equals 2x lambda, or x lambda equals 1. Therefore, x equals lambda over 1 over lambda. And similarly from this, you get y equals 3 lambda over 2. I keep saying the wrong thing. I mean 3 over 2 lambda. Okay, now when you plug these into the last equation, you get minus 1 over lambda squared minus 9 over 4 lambda squared plus 1 equals 0. For our own sake, let's multiply everything by minus 1, right, so that we don't have a bunch of minuses in front of the variable. Add them together. 1 over lambda is the same as 4 over 4 lambda squared. Therefore, you get 13 over 4 lambda squared equals 1. Lambda squared equals 13 over 4. And lambda equals plus minus square root of 13 over 4. So the first case, lambda equals positive square root of 13 over 4. And in this case, you get, put it back into these two equations, you get x equals what am I saying? You get x equals, well, why do I keep writing this? Square root of 4 is just 2, so it's just square root of 13 over 4, over 2. And x is 2 over square root of 13, and y is multiplied by 3 over 2, you get 3 over square root of 13. Okay, and in this case, we were trying to maximize, what was it? 2x plus 3y. So f of x and y. Remember that this is 2x plus 3y. This is 13 over square root of 13. This is square root of 13. And the second one, the second scenario, lambda equals minus square root of 13 over 2. And this gives us x equals minus 2 over square root of 13. Y equals 3 over square root of 13, minus 3 over square root of 13, and f of x and y, if you plug them in, you realize this is minus square root of 13. So obviously this one is maximum. And in fact, we actually also get the minimum, which is minus square root of 13 from this method. So this is why there's a step 2 in the process outlined above. When you find multiple solutions to the method of Lagrange multipliers, the only way to find the maximum or the minimum is to actually compute the value located at. We can also extend the constraint optimization problems to include more than one constraints, and we more or less follow the same process. For example, if we want to maximize or minimize f of x, y, and z subject to two constraints. First, g of x, y, z equals 0, h of x and y, z equals 0. Then you go through the same thing. So step 1 would be to define your capital F x, y, z. Now that since you have two constraints, remember we minus in our previous examples we subtract lambda times g from little f. Now, since we have two constraints, we need two Lagrange multipliers. The lambda is called the Lagrange multiplier. This is called what we are doing is called the method of Lagrange multiplier. This is just a clarification of the term. The lambda that we used in our previous problems is called the Lagrange multiplier. So in this case, since we have two constraints, we need two Lagrange multipliers. Let's call them lambda, and the second one is mu. Okay, and this is defined by f of x, y, z minus lambda times g of x, y, z minus mu times h of x, y, z. So it's pretty similar to the one constraint case, except that we have another term at the end. And then we do the same thing. We just take the partial derivatives of this capital F. Now we have 5 variables, so 5 equations, f partial x. Now I don't want to write x, y, z, lambda, mu every single time, so I'm just going to neglect the parentheses and just write f partial x here. So we have x partial x equals f partial y equals f partial z equals f partial lambda equals f partial mu equals 0. Okay, and step 3 is evaluate f at critical points obtained from step 2. Once again, the critical points are referring to the critical points of capital F, not little f. Okay? Let me just write it down. Critical points of capital F, and find Okay, so this is a Lagrange multiplier with two constraints. Of course, following the same logic, you can have a Lagrange multiplier with 3 constraints, 4 constraints, so on and so forth. You can have a general n constraints. So you just have n Lagrange multipliers. You have x subtracted by n terms. Okay, and you get n plus 3 variables. It will be a very large system of equations, but the idea is the same. You just subtract every single constraint from the original equation f and take partial derivatives, set them to 0, and last find the max and min. Okay, let's see an example. Find the minimum of this equation, this function f of x, y, z equals x squared plus y squared plus z squared, subject to x plus y minus 3 equals 0, and then x plus z minus 5 equals 0. Okay, so this is going to be our g, this is going to be our h, then our capital F of 5 things, of 5 variables, x, y, z, lambda, mu. This equals f, which is x squared plus y squared plus z squared, minus lambda times x plus y minus 3, then minus mu times x plus z minus 5. And then we take the partial derivatives of partial x. Once again, I'm going to skip the parentheses here to make the notation a little easy to read. Yeah. So f partial x equals 2x, then minus lambda minus mu. F partial y equals 2y minus lambda. F partial z equals 2z minus mu. F partial lambda equals minus x minus y plus 3. F partial mu equals minus x minus z plus 5. Oh, I forgot this is all 0 equals 0 equals 0 equals 0 equals 0 and equals 0. Alright, so we get a system of 5 equations. This is pretty easy to solve. I'm going to skip the calculations, but this is pretty easy to solve. For example, from this we know lambda equals 2y, this we know mu equals 2z, and then if you plug these into there, you can actually replace y and z with lambda and with lambda and mu. Anyways, you will get 3 equations with 3 variables and solve these, and then find the lambda and mu if you want. Alright, but the answer will be x equals 8 over 3, y equals 1 over 3, and z equals 7 over 3. Okay, we don't really care what lambda and mu are. I mean, if you solve the system, of course, you get values for lambda and mu, but that doesn't really play into the role of the final solution here. All we need is the value for x, y, z, and then plug it into our original equation, and the minimum of f, I'm going to write it like this, equals this squared plus this squared plus this squared. So it's 64 over 9 plus 1 over 9. This is not very good writing. Plus 49 over 9. So we get 114 over 9, which is 38 over 3. Alright, so this is an example for a Lagrange multiplier with 2 constraints. If you're interested, you can try a Lagrange multiplier with 3 or 4 constraints. It will be a lot more calculations, but the idea is the same. Okay? Alright, that's all for today. The web work's already been posted, and there will be another quiz 2 on Monday. Alright,